So we are still in part 2 of the class where we derive the governing equations of fluid mechanics. I told you before there are two important principles for this class. The first one being mass conservation and the second one being momentum balance. That will lead us to derive the momentum equation from the Navier-Stokes equation. And so we are starting this discussion today. And in particular, what we will do in here is to derive a statement of momentum balance, but at the control volume level. Note that the derivations in these videos are never complete, and I always refer you to the full derivations in the book, which correspond to your reading assignments here on the homeworks. Okay, so number 2. We're looking at the momentum balance and the momentum equation. The momentum balance at the control volume level. And so we will follow the same approach as what we did for mass conservation. And so let's consider flow. Again, here represented with just lines. There's only the streamlines or streak lines. I'm not telling you the flow is steady or unsteady. It's just supposed to represent flow. And now we define our control volume, which again is a completely arbitrary region of space. So this is our control volume. And our control volume is, the limits of these control volumes are a controlled surface. Whatever is inside the control surface is our control volume. Whatever is outside of our control surface is, well, not in our control volume. And we will assume that the control volume is not only arbitrary, but we here consider a control volume which is fixed in time. So the boundary here, the control surface, doesn't change with time. So again, I want to emphasize this control volume does not correspond to any, this control surface here does not correspond to physical boundaries. We're just imagining this control volume here, but this control volume includes a certain amount of mass, and therefore it is a mechanical system, and therefore we should be able to impose Newton's second law on this system, right? And so the question is, can we formulate a statement of momentum balance or Newton's second law on this control volume? Okay, so this here will be a derivation. All right, so if you remember high school physics, right? Newton's second law, mass times acceleration is equal to all external forces. But really, mass times acceleration is just, for a system with constant mass, a way of saying the rate of change of the total momentum is equal to the external forces. So if we're looking to make a statement of momentum balance on this control volume, the quantity we are interested in is how does the total momentum in this control volume change with time. So that will be the rate of change with time of the total momentum in the control volume. So what is that equal to? Well, if you just impose Newton's second law the way you know it, then you know that this has to be equal to the sum of, to the resultant force, to the sum of all external forces. Now, what kind of external forces do we have? Well, the first thing that you can think about are forces which you are aware of. So, for instance, the weight of the mass which is in here, and those will be body forces. So those are forces which are imposed onto material element of volume, differential material elements of volume, which are inside of my control volume. So the first external forces will be external body forces. Again, these are applied on the mass or on volumes which are inside of my control volume. Think of gravity. Think of if the material inside of my control volume was charged, that could be electric forces, or if you had magnetic spin, it could be magnetic forces, and so on. But then you don't have only external body forces. You really have to think about all of the forces imposed by everything which is not my control volume onto my control volume. And so in particular, this boundary here is arbitrary, it's imaginary, but you do have material here. And the material which is not in my control volume also imposes forces onto my control volume. Think about pressure, think about viscous shear, right? So if I'm only looking at the mass which is inside of this control volume, then I also have to consider as external forces the forces which are exerted by the fluid outside of my control volume onto the fluid which is inside my control volume. And these forces are exerted at the surface. So when you count all of the external forces to get to the resultant force, you also have to add external forces at the control surface. So we'll call these external surface forces. And it's important that you don't forget the external body forces and the external surface forces. Most importantly, because oftentimes it will happen many times that gravity is actually not so important, and that you don't have body forces on your control volume, and therefore the important forces that cause the momentum that influence the momentum balance of the mass which is inside of your control volumes are only the surface forces. Again, think about the pressure, think about the shear. We'll discuss a lot more of that in the coming weeks, but really realize that you do have external fluid here which exerts forces onto the fluid which is inside of our control volume. And when we're making the statement, we are interested in how the rate of change of the momentum inside of a control volume is related to the external forces. So that's what we have for now. And then there is a last term which we have to take into account. And we have to take this term into account because we picked a fixed control volume. Okay, so if we picked a material control volume for this analysis, then the boundary of a control volume would change, they would move, but the control volume would always include the same material elements. So there would be no mass transfer between the inside of the control volume and the outside of the control volume, because the control volume would follow the motion of the flow. Right? That would be a Lagrangian control volume. Here we have a fixed control volume, which means that elements of mass here, so mass which is inside of the control volume, flows outside of the control volume. And likewise, mass which sometimes is outside of the control volume flows inside of the control volume. Right? So there is a mass flow rate across the surface. Now, remember that every single mass which is in motion has momentum associated to it. Right? So when you were doing physics in high school, you had a point mass, and when that was moving, the momentum was the mass times the velocity. So if you have mass, then that mass has a certain amount of momentum. So when you're thinking about an element of mass here, a small dv volume with density rho, so rho dv mass, which is moving across the boundary, well, the momentum, which was associated with the mass m, which was inside of the boundary here, is carried out of your control volume. And so therefore, if you're thinking about how does the momentum, total momentum inside of my control volume change with time, well, you have to take that into account, because some of the momentum is going to leave my control volume and some of the momentum is going to enter my control volume. So the rate of change, you also need to take into account the flow of momentum across the control surface. Alright, so this is our statement put into words. Now, how do we translate that into a mathematical statement? So we're looking to derive now a mathematical statement of Newton's second law on a control volume. Now, before I go further, I want to correct something which I said before, right? Of course, here, because we'll talk about fluids, I'm saying assume that there is flow and that this is a fluid, but it doesn't have to be, right? Everything which I've written here, isn't only true for a fluid, right? It is true for really any continuum material, whether fluid or solid. So everything which I've written here is general to a control volume, which might include just solid material, a continuum material which is solid, or fluid. We haven't yet said what is the nature of the stress which the material which is outside of the control volume exerts on the material which is inside. So I just want to make that clear. If you want to think about fluids, that's fine, but in principle I haven't said anything about the nature of the continuum material at this point in this statement. Alright, so what is the rate of change with time of the total momentum in the control volume? So our control volume, we get our control volume where we integrate all of those little differential element of volume dV. So this is my differential element of volume dV over the entire control volume. So what is the momentum of this little control volume dV? It is the mass times the velocity of this control volume. So that would be rho u dV. That is the momentum of this small differential element of volume. And if I want the total momentum inside of my control volume, I have to integrate this over my entire control volume. Now this is the total momentum inside the control volume. And so if I want to express mathematically the rate of change with time of this control volume, I just take the time derivative. Again, because here I'm fixing my control volume and it's not changing in time, this quantity, the control volume is not changing in time. This quantity, which is the total momentum inside of my control volume, is only a function of time, and therefore I directly write straight derivatives. Now this, from Newton's second law, has to be equal to the resultant force, so the sum of all external forces. We discussed before that we have body forces. Body forces are imposed onto our differential element of volume, and the body force exerted on our differential element of volume dV we call usually a small f. This is a body force. This is a vector field which has units of newtons per meter cube. So if you want the total external force, the sum of all of the external body forces exerted on our control volume, we have to integrate over the entire control volume. Then we want to add all of the external forces which are exerted at the control surface. So we have to think and divide our control surface into all of those small differential element of surface ds. For every single one of these differential element of surface, we can define a normal vector, which is a unit vector pointing normal to the surface towards the outside of the control volume. And so we will be integrating, looking at our external forces exerted onto our ds, and the way we will write this is with a t bar, and this here is our stress vector. So it has units of a stress, so newtons per meter squared or pascals. And so again, what this stress vector represents, is the force exerted by the continuum material. So here the fluid or the solid on one side of this imaginary element of surface ds. And so the material which is actually outside of our control volume. And so it's the force exerted onto the material which is inside of our control volume on the other side of ds. So onto the material on the other side of ds. So inside the control volume. Now this stress vector you've seen before, and we'll discuss later on how we express it in terms of a stress tensor. What I will write for now is that it does depend, of course, on the position that we are in along the surface. It does depend on time, and it does also depend on the orientation of the surface ds. So it also depends on n. We'll discuss that more later on. Also note that this vector field here in principle could also be a function of x, potentially of t, dv. Okay, so this is the force exerted by the material on one side of ds onto the other for ds, and we have to integrate over the entire control surface. So we integrate here over a closed surface cs. So those are external forces, and then of course we have to take into account the flow of momentum across the control surface, right? So the question is, this term is going to be exactly like this term for mass conservation, right? So we first have to think, we're going to have to integrate the flux of momentum through the entire control surface cs. So we're going to have to integrate along the entire surface ds, right? And then the question is, how much volume crosses this surface ds per unit time? We've seen that before. That is our volumetric flow rate u dot n. This is the volume which is crossing ds per unit time. And then the question is, how much momentum is included in that volume that crossed the surface ds. Well, that is just rho u, just like here we said the volume in dv is rho u dv. This is the volume that crossed our interface, and so rho u times this volume that crossed the interface is how much momentum crossed the interface ds. Okay, and we're almost done, except that we have to think again about our signs, and just like what we had for the mass, we have a minus sign here. So I can rewrite this statement by putting, so I can put, this term, the flux term, on the left hand side, and that yields our statement of momentum balance at the control volume level. And so we have the rate of change of the total momentum inside of our control volume plus the flux of momentum coming out of our control surface cs, and that is equal to the sum of all forces on my control volume, including the surface forces. So the integral over cs of all of the forces which are imposed on all of the differential element of surface ds. So those are, this is my stress vector, this is the force per unit surface exerted onto my control surface, plus the sum of all of the body forces integrated over the entire control volume. All right, this is our statement of momentum balance at the control volume.